All right, we're back. This is page 1 of Calc C Notes 4. We're going to start talking about series. So this is called a series reintroduction. For some of you, you may have seen some of this before. Some of you may never have seen any of it before. I don't really know. I kind of start off as if you don't know anything, so you should be okay no matter where you're coming from. So basically, we did stuff about sequences so that we could talk about series, right? Like series is our goal. And so what we do is we take essentially, right, like 1, 2, 3, blah, 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 n. Those are all terms of a sequence. When you add up the terms of a sequence, you get a series. So it's just a sum. So it has this summation symbol, which everyone seems to think is the scariest symbol in all of math. I tend to agree with that. So it's a sum. So you might have had the sequence, right? So you would have the sequence A sub n, which is going to be, I guess, A1, A2, A3, dot, dot, dot. And then just go forever. And then a series, you just add them up, right? So we're adding up all of the terms of this. And so sometimes you're going to have the sum from 1 to infinity. Sometimes you'll have the sum from 0 to infinity. Sometimes you'll have the sum from 10 to infinity, where for some reason you're ignoring the first 9 terms of the series. But like whatever, you just kind of do what it tells you to do. And so if it really doesn't matter, which for a lot of our purposes, we're just interested, like, does it converge? Not what does it converge to, which is kind of weird and you have to get used to it. Sometimes you won't even see anything. It'll just be like, it's the sum of this stuff. So why we're going to do this, or at least how we're going to think about it to begin with, is we start with a sequence and we add up the terms, which gives you a series. And then you want to know, does the series, this is going to be a problem. Siri, yep, Siri just keeps popping up because series sounds a lot like it. I should just turn it off, but I don't really want to do that. I don't know. All right, so we're going to have a series, and our question is going to be, does it converge? To figure out if it converges, we start doing partial sums. So what's a partial sum? So here, if we're looking at this one, the partial sums would be, the first partial sum is just this term by itself. It's whatever a sub 1 is. The next partial sum is the sum of these two things. The next one is the sum of these 3. And then we'll add up 4 terms, and then 5, and 6, and 7. We'll see if, are the partial sums converging on something? So that's going to be a sequence. So we have a sequence of partial sums. And if the sequence of partial sums has a limit, then the series converges to that limit. It's not as hard to do as it is to talk about. So let's see if we can just write out some terms, because it's kind of a big deal. And then this says, if it's numeric, we can find the sum on the calculator, which is good because I don't want to do that by hand in almost any case. All right, so let's see. So we're just going to write out the terms. So first, because this is starting at 1, we take 1 and we plug it in, and that's going to give us 1/2 to the first, plus take 2 and plug it in, 1/2 to the second, plus take 3 and plug it in, 1/2 to the third, plus take 4 and plug it in. And then you stop. You stop because the upper bound is supposed to be 4. I'm going to do all these by hand, and then I'll go back and do them on the calculator just to get an approximation. Or I guess I can get these, whatever. We're saving the calculator for later. All right, let's see this. So here, there's just more stuff to plug in for. So when n is equal to 1, we get 1 plus 1 over 1 to the first. When n is equal to 2, we get 1 plus 1 over 2 to the second. When n is equal to 3, we get 1 plus 1 over 3 to the 3. And then we stop because the upper bound is 3. All right, so this you might almost recognize this as kind of being e. If n goes to infinity, we'll get e out of that. The limit as n approaches infinity of that is e. Which means that over time you're just adding plus e, plus e, plus e. So if we tried to go to infinity, there's no way we would get a finite sum, because over time you're just adding e. You basically get infinity times e, which is whatever. So that's a thing we want to think about. We don't need to think about it now, but I like to think about everything as much as I can. So let's see, we're going to start at 1. So we'll get -1 to the first over 1. And then we'll get plus -1 to the second over 2, plus -1 to the third over 3, plus -1 to the fourth over 4, plus -1 to the fifth over 5. So then you probably wouldn't write it this way. You would probably write this, and you would just like think it through. This is just going to be -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5. You want to get really comfortable with -1 to the n, because that's going to show up in like a third of all the series that you look at, right? So it just alternates positive, negative, positive, negative. It's a little faster to think of it that way. So here, almost the same, right? Here we have -1 to the n over n. Here we don't have that. We just have 1 over n. So it's easier to write out. But these two series are like a little bit different in their behavior. So 1 plus 1/2 plus 1/3 plus 1/4. So we'll see that these two series have very different, as you go to infinity, they have very different things going on. All right, we're almost at the point where we're gonna use a calculator, but let's do E and F. Now E is weirder than the ones that we've looked at, because there's another variable, there's an X, which is totally fine. So when you're doing a summation, down here, the index, which is what n is called, is telling you what you're subbing for. So it's not x equals 0, it's n equals 0. So x just hangs around. So what we're going to do is we're going to sub for n, and our answers will just have x's in them. So this is actually like a weird way of writing a polynomial. So -1 to the 0 is +1. Then you get x to the 0, and then over 0 plus 3. Now when n is 1, you get -1 to the first, which is negative. You get x to the second, and then over 4. So that was 1. When n is 2, you're going to get -1 to the second is positive, x to the fourth over 5. That's 0, 1, 2. When n is 3, you're going to, nope. When n is 3, you get -1 to the third, so minus x to the sixth over 6. And then finally, once something alternating is the best. Once it starts alternating, you can kind of forget about that -1 to the n, just like go with the pattern. And you can see like you're always adding 2 in the exponent, and then you're adding 1 to the denominator basically. So we'll get this. So this right here is actually a polynomial. It's an 8th degree polynomial, and because the coefficients had a pattern to them, you could write this thing as a summation, which is so in general, like algebra 2, algebra 1 type, in general, it's like really hard to write a polynomial with like a pattern to the coefficients. When you start talking about series, we already saw this with Taylor polynomials, it's actually not that hard to do. And that's because there's a very specific pattern to some of the coefficients. So this is also going to give me a polynomial because of this x to the n. So let's see if we can do this. You typically don't expand things like this though. So I'm going to write this is equal to, when n is 0, you get x to the 0, which is 1 over 2 to the 0, which is 1, and 0 factorial is 1. So you just start with 1, and then plus x to the first, 2 to the first, 1 factorial. You don't need to write 1 factorial, but because you're always like pattern seeking, it's a good idea to do it. We'll get x squared, 2 squared, 2 factorial, x cubed, 2 cubed, 3 factorial, x to the fourth, 2 to the fourth, 4 factorial, x to the fifth, 2 to the fifth, 5 factorial. Okay, and so eventually, not now, but eventually we're going to want to try to figure out, like, is there a function that we're approximating here? This one, I think, if I'm not wrong, I think that this is going to be approximately e to the x over 2. I think they will approximately look the same. Maybe we'll look at that. All right, so let's go to the calculator. I'm going to have the calculator. I'm just going to, in case you've never done it before, we're going to do summation. And then also I am going to like take a look, I think, at that other, at that last one. Does it look like something we know? So templates, there's a summation template. Get to love it. N is 1, 2, 4. And then you type exactly what it looks like. So there's no real ambiguity here. So 15 over 16, definitely could have done that one by hand. Probably should just know that, but I definitely don't. Let's try it again. All right, so summation, we're gonna go from 1 to 3, and we got 1 plus 1 over n to the n. Okay, so 715. So if you have a finite number of terms, so like the upper bound on your summation is not infinity, then you actually are pretty much always going to get a sum, unless unless there's vertical asymptote or some weird thing in the function in there, which is an important idea. Going to infinity, all bets are off. Finite sums, you're going to be able to find a sum. So here we go, n1 to 5, -1 to the n over n, -47 over 60. Just writing these down as I go. Okay, and now it's not going to alternate, so I can actually just go up here. So I could just make this to the 2n, because -1 to the 2n is only, it's always 1, it's just +1. So this is 137 over 60. Okay, so far so good. Let's see what the calculator does with this weird one. So it's going to have x's in it. Calculator knows what to do. Like it's pretty smart. We get -1 to the n. So the thing about the calculator is it can only be as smart as you are, because you have to know what to ask it. But as long as you do, so we get this. You can see this is in the opposite order of what we wrote down, though, which is what's going to happen every time you do a finite summation. It's always going to write it in like standard form, where it goes highest degree to lowest degree. But when you do your Taylor polynomials, it was doing lowest to highest, which makes sense because it's supposed to do that. It knows to do that. And then finally on the page, n goes from 0 to 5 of x to the n, 2 to the n, n factorial. And we get this. Okay, so this is what we wrote. It doesn't exactly look like it, but it definitely is. I was saying that I think this is actually the Taylor polynomial for e to the x over 2 x, and then I think it's the 5th degree Taylor polynomial. And you can see that it is. So this does equal this. So one of the things we want to be able to do is look at these summations and figure out what functions they're actually approximating, potentially. So I can tell you, it's not really relevant exactly right now, but I can tell you how I figured out that this was going to be e. The way I figured it out, if you remember all of those polynomials that you memorized, the denominators had, a lot of them had factorials, right? Sine, cosine, e had factorials. Only e had n factorial, right? Cosine is the quantity 2n factorial. Sine is the quantity 2n plus 1 factorial. E has n factorial. So in my mind, I rewrote this as x over 2 to the n over n factorial, right? And as soon as I did that, I said, that looks a lot like e, but instead of e to the x, it looks like we subbed in x over 2 for some reason. So it looks like e to the x over 2. So that's a thing that we want to be able to do. But that's in the future. Not in the far, far future, but a little bit in the future. So the last two were actually polynomials. They weren't numbers, right? You didn't get a final number out of them. But the other ones are just numbers. Finite series, you're always going to get a sum. Go to infinity, all bets are off until you work it out, and then feel very confident about betting once you work it out. But anyway, I'm going to stop this here. I will come back in the next one and do some more. So see you there.